In this video, we'll continue to look at electricity. Now, previously, we would have looked at static electricity or electrostatics. Today, we're going to be looking at what is called current electricity. Alright, so we're going to be looking at current electricity. Now, before we go into current electricity, let's do a brief recap of static electricity. Now, or electrostatics. The word static basically means stationary or not moving, right? So when we speak about static electricity or electrostatics, we're talking about the branch of electricity which deals with charges which only flow for brief periods or charges which are stationary. So once again, when we speak about static electricity or electrostatics, we're generally concerned with charges which are either stationary or which only flow for brief periods, right? However, in this case, we're going to be looking at what is called current electricity. Now, before we jump into the specific requirements of the syllabus, let's do a brief comparison of current electricity and static electricity. Now, we know that basically electric current is due to the movement of charge, right? Now, electric current is basically due to the movement of charge. So in order for an electric current to flow, charge must move. Now, when we talk about static electricity as opposed to current electricity, as we mentioned before, static electricity basically involves charges which are stationary or which only move for brief periods. Whereas current electricity, as we will see, will involve charges which are basically on the go. They're basically continuously moving, right? So once again, static electricity or electrostatics deals with charges which are either stationary or which only flow for brief periods or move for brief periods, whereas current electricity deals with charges which are basically moving for much longer periods. Now, one analogy I often use basically with static electricity versus current electricity is this. If you think of the water in a pool. Now, if the water is in a pool, it is basically stationary. If you jump in the pool or throw something in the pool, the water is disturbed for a brief time. The water will basically move about in the pool, but eventually it settles back down and stops moving. If you compare that to, say, a flowing river. In a river, the water is flowing, and so therefore there is a current, right? So essentially, in this analogy, the water in the pool represents the static electricity and or the charges during static electricity, and the flowing river basically represents current electricity, right? So once again, the movement of the water basically creates a current in the river, similar to how the continual movement of the charge basically creates the current, the current electricity, as opposed to in the pool, where the water is basically stationary for most of the time, but if disturbed, it can actually move for a short amount of time, similar to charges when we look at static electricity, right? So with that said, now let's basically jump into what the syllabus requires us to do. So the syllabus basically expects us to be able to look at conductors and insulators. So let's look at conductors versus insulators, right? So conductors versus insulators. Now, when we looked at heat, we would have met these terms before. So we would have met a conductor, and we would have also met insulator when we looked at heat. So let's try to refresh our memories, right? So in our look at heat, we basically said that a conductor was a material which readily allowed heat to flow throughout that material, whereas an insulator was a material which basically did not readily allow heat to flow. So we generally would have said that materials like metals are very good conductors of heat, and that is why, for instance, our pots and our pans and our baking trays are made of metals, whereas their handles are made of materials like wood or plastic, and these materials, wood and plastic, are not very good conductors of heat. We say that they are insulators. So when it comes to electricity conduction and, say, thermal or heat conduction, there are similarities between these different types of materials, conductors and insulators, right? So once again, when we spoke about heat, we said that conductors readily allowed heat to flow, and of course, whereas insulators did not readily allow heat to flow insulators did not really allow heat to flow, right? So once again, let's compare them. So we say that conductors readily, well, in this case, we're talking about electricity, right? So when we speak about conductors, then of course we're going to be talking about conductors and insulators. We're basically going to be comparing the relative ease with which an electric current will flow through each of these materials. Now, before we go deeper into conductors and insulators, let's talk a little bit about charge, right? Let's talk a little bit about charge. Now, we have mentioned before that basically charge is possessed by protons and electrons. And of course, we look at the simple version of the atom. In a simple version of the atom, there is a centrally dense portion called the nucleus, which of course consists of, say, the protons and the protons and the neutrons, right? So let's put some random numbers here. So protons and neutrons. Now, the protons are positively charged, the neutrons carry no charge, and of course, they are strongly bound within the nucleus of the atom. Now, there are also electrons which are less strongly attached to the atom. They're more loosely attached to the atom, and they are basically can be found circulating on what we call shells, right? So these X's basically represent the electrons on their shells. So we can think of the shells as circular orbits around the nucleus of the atom. Now, because electrons are more loosely connected to the atom, it means that basically they can move within the atom from place to place, and they also have the ability to jump from one atom to another. Now, this ability of electrons to move from one location to another is basically what gives bodies the ability to become charged, and is also what is responsible for electric current flow, right? So we'd have looked at charging, for instance, by induction, charging by friction, and of course what is enabling this type of charging to take place is the ability of electrons to move. So once again, it is the ability of electrons to move which allow bodies to become charged and also allow electric current to flow, even if only for brief periods, right? Now, having said that, we will continue or look at conductors and insulators, right? Now, what is a conductor? When we speak about a conductor when dealing with electricity, we're talking about a material which basically readily allows an electric current to flow. So a conductor readily allows an electric current to flow, right? So a conductor readily allows an electric current to flow. In the case of the insulator, it does not readily allow an electric current to flow, right? So a conductor will readily allow an electric current to flow, whereas an insulator, as I said, it simply does not. So I'll just put does not. So the insulator does not readily allow the flow of an electric current, right? So once again, similar to how in terms of heat, a thermal conductor will basically really allow heat to flow through the material, and insulator will not really allow heat to flow. And it's the same principle when it comes to electricity, right? So let's speak about electrical conduction. A conductor will readily allow an electric current to flow, whereas an insulator does not, right? Now, what else do we know? What else do we know about conductors? Now, what we need to understand is this: different materials can and do conduct electricity, right? So different materials can and do conduct electricity. So for instance, water can and does conduct electricity. And of course, if your hands are wet and you come in contact with some raw wire, then you're likely to get an electric shock, right? So water can and does conduct electricity. However, when we use the word conductor, we're typically referring to metals. So as a matter of fact, in many cases, you might see the expression metallic conductor, so as not to cause any confusion. But typically, if you don't see the word metallic and you just see conductor, then usually, of course, you're referring to metals. So conductors, we can say that are metallic. And of course, examples of conductors, for instance, would be copper or aluminum, right? Which of course are two metals, right? So conductors are metallic, example copper and aluminum, whereas insulators are non-metallic, right? Now, being metals, it also means that conductors will contain free electrons. So conductors will possess free electrons, whereas insulators do not possess free electrons, right? So these are basically a few differences between conductors and insulators, right? So that basically conductors will readily allow the passage of an electric current. In other words, they will readily allow charge to move through them, whereas insulators do not. Conductors are usually metals or metallic, and of course, example, copper, aluminum. Insulators, of course, are non-metals. Being metals, conductors will contain free electrons, which of course is one of the reasons why conductors are very good at conducting not only heat but electricity, right? This is due to the presence of the free electrons, whereas insulators do not possess free electrons. Now, whenever we deal with electricity, we often come across, for instance, connecting wires, and many times our connecting wires, of course, are covered in some type of material like rubber, right, or plastic. So when we speak about insulators, of course, being non-metallic, of course, these typically include rubber or plastic, right? So these are typical insulating materials. So we have a connecting wire here, and of course inside it we have the metal part is of course usually copper, and of course we have this plastic outer covering, which of course is used to insulate the conductor, right? So I mean, usually of course we have I guess you could call it I don't know is the wrong word here. Well, we have conductors and insulators basically used in together, right? All right, so we're able to look at conductors and insulators, right? All right, so having looked at conductors and insulators, we're going to now focus on electric current, right? Let's talk about an electric current. Now, what is an electric current? Now, we probably would have touched on this before, but let's give basically a formal definition for an electric current. An electric current basically is the rates of flow of charge, right? So an electric current is a rate of flow of charge. The symbol for an electric current is an uppercase I, and the SI unit is the ampere. Symbol for the ampere, of course, is an uppercase A, right? So an electric current is a rate of flow of charge. The symbol for an electric current is the uppercase letter I, right? The SI unit of electric current is the ampere, which of course is one of those quantities which was named after famous men who did work in these particular areas of physics, right? So previously we'd have met the joule, would have met the watt, would have met the Newton, which of course are all the names of famous people who did important work in particular areas of physics. The ampere is also one similar unit, which of course is named after the man who did a lot of work in electricity, right? So an electric current is a rate of flow of charge. The symbol is the I, uppercase I, and of course the SI unit is the ampere, right? Now, according to the syllabus, we need to be able to appreciate or state that electric current in a metal consists of a flow of electrons. So we did briefly look at the atom, and we said that basically within the atom there are protons and neutrons which are strongly bound within the nucleus. Circulating the nucleus on shells are electrons which are more loosely attached to the atom. Now, we also mentioned the fact that in conductors, which of course are usually metals, there are free electrons, and it is the ability of these electrons to move which basically makes conductors or metallic conductors very good, not only very good conductors of heat, but also very good conductors of electricity. So generally, metals are very good conductors of heat due to the presence of free electrons, and they are also very good conductors of electricity due to the very presence of the free electrons. Now, when we deal with electric current, as I said before, it is the rate of flow of charge. And as we established before, when it comes to an atom, the protons are very strongly bound within the nucleus, and it is therefore the electrons which are able to move and are responsible for an electric current flowing. So whenever we talk about an electric current flowing, especially in a conductor, we're talking about the movement of electrons or negative charges. Now there are other situations in which not only negative charges, that is electrons, will flow, but also positive charges as well. But in the case of metallic conductors, it is the electrons or the negative charge carriers which are actually responsible for the electric current flowing. Later on, we will look at semiconductor materials, and of course we will probably talk about the different, in addition to the negative charge carriers which are electrons, there are also positive charge carriers called holes. But at this level, at this stage, we don't need to focus too much on that, right? So basically, electrons are not the only type of charge carriers, but at this stage, we're going to be focusing on the movement of electrons as the primary charge carriers. But of course, do understand that there also can be positive charge carriers, typically called holes, and of course, we'll talk about them when we look at semiconductors, right? Now, the syllabus also wants us to look at what is called conventional current, so we will look at what is referred to as conventional current, and of course we'll talk about what differentiates conventional current from the movement of electrons. Now, to do that, we will basically draw a simple circuit. Now, let's examine this circuit here. We have in our circuit a battery. Now, as you may know, a battery is basically a group of cells, right? Now, let's put in our circuit a resistor, and let's just close our circuit, right? So this is a symbol for a battery. Now, a battery is a group of cells. So a cell is simply a single long stroke and a short stroke, and a group of cells is basically a battery. So when we have our circuit here, there is a battery, right? So we have our battery, and in the circuit, because we basically have our circuit here, and we want to look at what is called conventional current, right? So I want to look at conventional current. Now, as I said before, this is our circuit. Now, this is our battery. This, of course, is the negative terminal of the battery, as indicated by the shorter stroke. And this is the positive terminal of our battery, as indicated by the longer stroke. Now, whenever we have a circuit like this, we often show the current that is flowing in the circuit. The current is normally shown to be flowing from the positive terminal of the battery, and of course is indicated by the uppercase letter I. So with a circuit like this, we would draw the circuit, and we basically show the current flowing around the circuit in this direction. I guess that would be anti-clockwise. So the current is basically seen to be flowing from the positive terminal of the battery around the circuit, and of course back to the battery. Now, we do know that electric current is actually due to the movement of electrons, right? So we established that basically in an atom, the positive charges basically don't move that easily. The protons are basically bound within the nucleus of the atom, and therefore they do not move, right? Now, then why is it that we show electric current flowing from the positive terminal of the battery as opposed to from the negative terminal? Now, let's talk about the electrons for a while. Now, basically, when it comes to a battery, we have a positive and a negative terminal. The negative terminal of the battery is basically where there is a surplus of electrons. There is a surplus of negative charges, And as a result, whenever battery is part of a closed circuit, electrons, of course, will then move in this direction. So electrons, of course, will move from the negative terminal of the battery and flow around the circuit, and of course will be deposited to the positive terminal of the battery, where of course electrons are in short supply. So remember this, a surplus of electrons basically results in a negative charge at this terminal, and electrons being deficient, or the absence of electrons, basically results in a positive terminal, in the positive terminal of the battery. So when you connect a battery to a closed loop in a conducting path like this one, then it is actually electrons which move around the loop, which are basically responsible for the electric current. So we do know that electric current is a rate of flow of charge, and because the mobile charge carriers are electrons, essentially electric current is a rate of flow of electrons. Then if that is the case, then why is it that we see current flow being shown from the positive terminal of the battery going in the opposite direction to that in which electrons will flow? Now, there was a time when a lot of things that have been discovered that we know about now were not discovered as yet. And of course, when the work was being done on electricity, it was initially thought that electricity or electric current was due to the flow of positive charges. And therefore, it was accepted for quite some time that an electric current was due to the flow of positive charge. However, it was then later discovered that the positive charges, the protons, were strongly bound within the nucleus of the atom and therefore did not move. It was the negative charges, the electrons, which were actually able to move and therefore responsible for the flow of an electric current. However, by this time, it had long become accepted as a convention that electric current was due to the flow of positive charge, and as a result, up to this day, we still see electric circuits being drawn essentially with the current flowing from the positive terminal of the battery. And this, of course, is said to be conventional current, right? So when I speak about conventional current, we're talking about the direction or electron flow, not electron flow rather, but current flowing in a direction that positive charge would move. And of course, conventional current is always in the opposite direction to electron flow. So in any particular circuit, if electrons move in one particular direction, say clockwise, it means that the conventional current must be flowing in the opposite direction. And typically, when drawing a circuit, we show the conventional current indicated by our letter I, and it basically flows from the positive terminal of the battery, right? Now, having spoken about conventional current, of course, as I said, in our circuits, it is really conventional current that we're typically expected to show in our circuit diagrams. But of course, you can always be asked to show the direction that electrons will be moving as well, right? Now, we define electric current. We state the symbol, which is I, and of course, we state the SI unit as well. The syllabus also wants us to look at equation required to basically calculate electric current. Now, as mentioned before, an electric current is a rate of flow of charge. Now, we would have met charge before. The symbol for charge is Q. So the symbol for charge is Q. And based on the definition, electric current is a rate of flow of charge. Usually, when we include the word rate in any definition, it implies time. So when we speak about electric current being the rate of flow of charge, it is essentially the charge flowing per unit time. And as a result, the formula which relates electric current, charge, and time is given as this, or the equation I is equal to Q over T. So the equation which relates current I, charge Q, and time T is I equals Q over T. And of course, you could always rearrange this equation so we get that Q is equal to IT, right? Now, if we look at the right-hand side of this equation, the SI unit of charge is the coulomb, and the SI unit of time is the second. So basically what this is telling us is that the ampere is actually equivalent to the coulomb per second, right? So because the SI unit of charge is the coulomb and the SI unit of time is the second, if the SI unit of current is the ampere, then basically what this is saying is that 1 ampere is equivalent to 1 coulomb per second, right? So when I speak about a current of 1 ampere, what that basically means is that 1 coulomb of charge would basically flow for 1 second, right? Now, the syllabus might not require us to know those definitions, but of course, knowing them don't hurt, right? So in terms of, let me see. Right, so basically the syllabus expects us to be able to apply the equation Q is equal to IT, unit of charge, right, can be obtained from this equation, right? Good. So as I said before, the SI unit of electric current is the ampere, and of course the current is given by the equation I is equal to Q over T, and from this equation we basically get that 1 ampere is equivalent to 1 coulomb per second. Now, using this version of the equation, of course, we could always rearrange to get the unit of charge. So Q is equal to IT, then therefore this would mean that 1 coulomb will be equivalent to 1 ampere times 1 second, right? So in this video, we were able to look at conductors and insulators. We're able to talk about electric current, conventional current direction as opposed to the direction of electron flow, and we're able to look at the equation which relates electric current, charge, and time. Yeah.